this work, I'm Sylwester Arabas. He got his PhD from University of Warsaw in Poland, where he was one of the early adopters of particle-based schemes for modeling clouds. After that, he ventured off to work outside of academia as a quant in science or in finance, but then decided to come back to Poland, to Jagiellonian University, where he's starting his own research group, modeling clouds. And this year he's spending in United States at the University in Illinois, Urbana-Champaign, working in the group of Nicole Rimmer. And he's going to present his results on supercooling super-droplets.
Thank you. Thank you for coming. Thank you for the opportunity. This work is done with collaborators from University of Illinois, as well as Penn State, NASA GIS, and Stony Brook. And as Anya introduced, besides representing the Atmospheric Sciences Department at UIUC, I'm also affiliated with Jagiellonian University in Kraków, Poland. And this work is funded from Department of Energy ASR program. So let me start by painting a conceptual picture of aerosol-cloud interactions that are the set of phenomena that we want to address generally with the methods I will be speaking about. So the conceptual picture, I would argue, looks as follows. So what we see here is actually a complex system of processes that one may say start with the emissions of aerosol particles into the air, be it from natural, anthropogenic origins. These particles acting as nuclei in processes such as condensation and crystallization, upon which the water phase changes and subsequently also causes growth of the nucleated particles to form larger droplets, ice particles. These particles are also subject to collisions, aggregation in the clouds. And finally, or concomitantly, there might be aqueous chemical reactions occurring in this kind of cloud system, as pictured there. When these particles reach sedimentation velocities, causing them to precipitate, they might on the way break up into smaller parts, and also they might interact with the aerosol population under the cloud by washing the aerosol. Finally, not all particles reach the ground. Those that precipitate and evaporate on the way are contributing back to the ambient aerosol population, potentially having been altered through the physical and chemical processes occurring in this system. So I'd say that for this talk, the key takeaway here is that these are two-way interactions. So the aerosol particles influence, define the properties of clouds, while the clouds itself effectively alter the aerosol population through this cycle depicted in this picture. So when we embark on challenge of modeling these processes, we have choices with respect to the way how to represent, how to discretize the phase space and how to represent the dynamics occurring in this phase space. So first of all, let me just say that we are here working with continuous phase and dispersed phase. The moist air budget. So here, let me assume that the dynamical is there and not worry about it. I'll focus on the dispersed phase. And here we are faced with representation of particles that span large span of sizes, from aerosol particles down to nanometers, through cloud droplets, micrometers to tens of micrometers, drizzle droplets that have significant size, yet not significant fall velocity, and rain particles that are subject to precipitation. This is just for liquid. Of course, if we add ice phase, this gets even more complex and spans, let's say, more dimensions in such attribute space. So when discretizing such a system, we in principle have two fundamental approaches. We can go the Eulerian way by assuming that sections into which we discretize the probability density function describing our particle size distribution is represented by a set of beams or sections. And in the Eulerian approach, when we think of the PDF on the y-axis, particle size on the x-axis, we fix the locations of the beams, and the dynamics of growth processes alter the magnitude of these beams. The alternative is Lagrangian representation, when in the same phase space, we actually fix the magnitude for a simple growth process, and we alter the position. So this would work, for example, for this case depicted here of growth of population of particles through condensation of vapor onto them into larger sizes. When we start modeling more complex processes, as depicted in the previous slide, we need more attributes. Our attribute space is multidimensional. These dimensions can be, for example, as depicted here, the particle size, particle phase, habit, composition, and finally, location in space. So here, I added these dimensions, and in principle, thinking in this Lagrangian spirit, I'm renaming this approach to superparticle or particle-based representation. So it is still the Lagrangian approach in terms of the movement in the phase space. However, now we extend our list of attributes from just size to other attributes, including positions of the droplets. So what we achieve is a model that is a coupled system of an Eulerian component responsible for fluid dynamics and a Lagrangian component that is responsible for the properties of the particles that drive the aerosol-cloud interactions that we want to capture. And there is a bidirectional coupling. So the flow moves the particles might influence the flow through both momentum exchange and heat exchange through the attributes assigned to the particles. So having introduced it and being motivated by some of the discussions we had last week here, I thought of bringing here a list of few works that are probably selected in a very non-representative way, but that might give a hint of how we ended up at the place where we are now in terms of thinking of the ways of representing microphysics. So going back to early kind of times of numerical modeling, notably times where authors wrote about computers, not computers, we can arguably say that the very first numerical study of cloud microphysics used this moving sectional approach. So the work of Howell from 49 uses 7 classes of nuclei, and each class is a group of uniform drops. So I would say that the moving sectional approach was kind of first. Then by 70s, we developed already systems aimed at capturing a lot of the phenomena that occur in the air. This work is not directly relevant for cloud modeling. However, it uses this Eulerian-Lagrangian coupling for representing marker particles tagged with coordinates and age since generation, mass, activity, species, and size. The authors note that such Lagrangian Eulerian coupled simulation is characterized by no numerical diffusion in the attribute space. For those of you working with fluid dynamics, with bin representation, it's an important aspect. And actually also the performance of this method is mentioned as the advantage. So here it's relatively fast running, in part because computations are only made for those cells that contain particles. So this is something that characterizes this Lagrangian method, that they are kind of solution following. So if you start with discretization that is located around the interesting locations in your phase space, your solution will advect your discretization along the places of interest, let's say. So let's imagine we are thinking of cloud condensation nuclei. We have a large spectrum of aerosol, and we know what is the size range that is around our cutoff size for activation, unactivation, haze particle, activated particles, etc. We can place a lot of beams around this region, less at the tails, and this will lead the solver to follow our solution with growth of the droplets towards larger sizes. And of course, also it works with other attributes such as space. So if we have cloud in, let's say, 1% of our domain volume, we might consider populating just this part of the space with particles to represent clouds, or air dispersion as in this work. And by the 80s, we can already find papers which added Monte Carlo techniques to this picture, where one model output represents just one realization. And this is the work that I think is the first that mentioned superparticle term in the context of atmospheric modeling. So superparticles here are some particles, simulation particles representing cloud of physical particles having similar characteristics. So essentially what was before, but now introducing this Monte Carlo, so probabilistic approach. So jumping to 21st century and looking at a reference book on atmospheric modeling, we go to a section devoted to the ways of discretizing size distribution. And what we referred here is they're called the full moving structure, analogous to Lagrangian in horizontal advection. The advantage that the core particle material is preserved during growth. This is the very thing that enables us to capture this bidirectional aerosol-cloud interaction. So we can retain the identity of particles throughout all these processes and be able to, for example, resuspend processed aerosol after chemical reactions, collisions, breakup. So it goes back to the aerosol population, having traced all processes on the way. As in the earlier work, elimination of numerical diffusion is important for these methods. However, due to problems representing nucleation, coagulation, as of this time, these methods were summarized not to be usable in 3 dimensions. What is the problem with coagulation? Well, basically, this is the solution following aspect. So if we have 2 particles that collide, after collisions, their location in the phase space changes to another place. So this is kind of a non-local dynamic. And if we have 2 particles, they are superparticles, so they represent a lot of real-world particles. Part of them collides, and we need new memory, new particles to represent the output of collisions. Similarly with nucleations. So arguably, one of the first works to overcome it in cloud modeling context was a work of Shinichiro Shima and his team from 2009, introducing the super-droplet algorithm, which is a Monte Carlo scheme that solves this coagulation problem and applies coupled Eulerian Lagrangian setting for simulation of cloud microphysics, warm rain process. So super droplets, according to Shima, is a kind of a coarse-grained view of droplets, both in real state and attribute space. And again, the cost becoming lower than beam methods is suggested to be one of the reasons to use this method. Interestingly here, with a theoretical analysis, the authors estimated that if the number of attributes is 2 to 4, we are already gaining in terms of performance compared with bin methods. And please remember that location in space is part of this attributes set, meaning that even the basic set of attributes, for the basic set of attributes, one might expect essentially speed up with respect to bin spectral methods. Why? There are several aspects here from the integration aspects of the equations that arise in such problems to parallelization aspects, etc. However, in simple terms, I would say that the fact that we move from partial differential equations to ordinary differential equations is one of the keys to this thing. We are also avoiding the curse of dimensionality. So the bin methods scale with every new dimension added, so with every new attribute added, our phase space and our discretization space scales exponentially. With the particle-based methods, every new attribute is just another attribute of a particle, and representation of processes such as coagulation, such as transport, scales linearly with the number of particles. So this was the beginning of 20th century, and 10 years later, looking at a review paper by Morrison et al., 2019, the particle-based methods are listed as one of 3 alternatives for representing cloud microphysics, on par with bin, so the Eulerian size methods, and bulk, multi-moment bulk methods. So with this, I kind of covered the conceptual picture of aerosol-cloud interactions, the Eulerian and Lagrangian approaches to modeling cloud microphysics. And now let me move on closer to the title, the topic, that is immersion freezing. And here I'm kind of titling this part as singular versus stochastic. So here in a figure from Zamin Kanji's review paper on ice processes in clouds, we see a sketch of a multitude of processes leading just to formation of ice in clouds. This actually doesn't even count the feature the later evolution of this particle. This is just how the ice is formed in clouds. So on the y-axis here, you see the temperature going downwards. So we have warm air here, the 0 isotherm, above which formation of ice is possible, and minus 38, which is a threshold for so-called homogeneous freezing. So at this point, freezing occurs for water in a spontaneous way without any catalyzing factor. And here, between minus 38 and 0, we have a range of processes that might result in formation of ice at higher temperatures, closer to 0. So before we dive into it, let me place here, put emphasis on a work that actually triggered the project I'm covering here. So in 2020, the group of Shima, the author of the earlier paper I mentioned for the kind of seminal work in super-droplet modeling, in 2020, they published a paper describing ice phase, mixed phase, cloud microphysics using the particle-based approach. So in this work, they use a coupled Eulerian Lagrangian system. The Eulerian component, CFD component, is responsible for the budget of momentum, heat, and moisture. The Lagrangian component are these super particles representing aerosol, water droplets, ice particles. So it's important to note here that in such models, particles during the simulation execution are not arbitrarily categorized into these droplets or ice or aerosol. So they are assigned with this attribute that in most cases have continuous spectrum of values, and just the values of these attributes for us in, let's say, post-processing of the simulation data allow us to categorize these particles if they are small, aerosol, liquid and larger, droplets, yet larger, drizzle, rain, or ice. For the ice phase, this model uses the so-called porous spheroid model, which is based upon geometric description using two axes for representing the diverse shapes of ice particles. Well, when it comes to the processes represented, the particle resolve component here represents advection and sedimentation of particles, homogeneous and immersion freezing. The immersion freezing is done using the so-called singular approach, which I will elaborate more on next slides. There's also melting of ice, condensation and evaporation, and this includes CCN activation. So since aerosol and droplets are not distinguished arbitrarily, they are all subject to condensation and evaporation, which covers the phenomenon of this bifurcation in the spectrum due to reaching critical radius and embarking on positive feedback growth regime. We have then deposition and sublimation, and finally collisions. And again, collisions in this model is represented as a single process in this Monte Carlo probabilistic way. And this covers what we would name with a nomenclature such as coalescence, rhyming, aggregation, washout, depending on which particle collides with what kind of another particle. So if a large rain droplet collides with aerosol under the cloud, this is washout. If two droplets collide, we have coalescence, autoconversion, etc. However, from the point of view of formulation, these are just collisions. And the paper features a two-dimensional cumulonimbus test case depicted here on the left with monodisperse ice nucleating particle assumption. So onwards in this talk, I will comment on the immersion freezing representation with the singular model and on the monodispersed INP assumption. So going back to our picture of the processes that lead to formation of ice, we now focus on immersion freezing. So what is immersion freezing? Basically, we start with activation of droplets below the zero isotherm. So we activate the droplets, and we know that here inside, we depict an insoluble particle. So even though it's within a droplet, it remains not dissolved. When it crosses the zero isotherm, at some point, it freezes before reaching -38. So in temperatures warmer than -38. When we would compare it with activation of purely hygroscopic substance, as note that homogeneous freezing without the insoluble core happens at lower temperatures. Is it important for life, for us? Well, bacteria and the Olympics. Any suggestions what the slide is about? Immersion freezing. So, 2016, I believe, a recent study unstable ice nucleation properties of SNOMAX bacterial particles, and the authors find that immersion freezing properties of SNOMAX particles are substantially unstable, observing a loss of nucleation ability under certain conditions. And this is why it's important. So actually, the physical basis of operation of a snow cannon is immersion freezing. What this instrument does, it uses high pressure nozzle spraying of water, contaminated either naturally or with some specifically added material as the SNOMAX registered trademark. And the cannon spits small droplets of water that when reaching lower temperature, freeze at temperatures even close to 0 degrees Celsius because of presence of the immersed nuclei inside of SNOMAX bacterial matter. That is a very efficient nucleating agent. So continuing on
Sylwester,
Yep.
I have a question. Is that okay?
Sure.
Okay. Andy Ingersoll asked, how do you handle collisions when you are using super droplets, which I assume means having fewer droplets per unit volume than in reality?
So thank you for the question. The super droplet representation is a Monte Carlo algorithm in which first, among a population of superparticles, each representing a multiplicity of real-world particles, selects candidate pairs for collisions. So let's say we have 100 super droplets within a sampling volume. So we divide it by half, and we consider 50 pairs of particles for collisions. For these 50 pairs, we toss random numbers. We evaluate probability of collisions given a multiplicity of a given super droplet, given the ambient properties, and given the attributes of the droplets, such as size, which determines the cross-section for collision. So having the random number and the probability, we compare it, and we trigger collisions according to the probability. But instead of colliding, let's say 10% of droplets represented by a given superparticle, if the probability would be 10%, we instead collide all the particles within a given superdroplet, but only once per 10 time steps. That leads to this 10% of probability. So in short, this allows us to first conserve the number of superparticles, and second, maintain linear computational cost scaling with the number of particles. I hope this was addressing the question.
Yeah, that was great.
Whatever time, soon or after the talk. And let me move on with this slide and mention also some of the early works on immersion freezing. So one of the seminal papers here is the work of
Bluetooth pairing.
Bernard Vonnegut from 1948. And I'm bringing it here because I think that the plot here not only historically nicely depicts the problem, but also is a very good depiction of the challenges for modeling. So on the x-axis, we have time in minutes, y-axis, the number of liquid water drops, so the drops that remain unfrozen. And we see that we have three different curves. These curves differ by the ambient temperature. So minus 18, minus 16, minus 30. We see that the ambient temperature is the key to triggering the freezing. On the other hand, we also see that for a given temperature, the process is dependent on time. So the longer we wait at a given temperature, the more we freeze. So intriguingly, 60-something years later, when we look at the review paper on immersion freezing, Gabor Valley 2014, interpretations of the experimental results face considerable difficulties. Two separate ways of interpreting the same observations. One assigned primacy to time, the other emphasized the temperature-dependent impacts of the impurities. So these are the modes that make the droplets freeze. So we have a dichotomy of the stochastic and singular models to describe this experiment. So basically, I would say that what is written here, we could kind of see in Vonnegut's paper already, simplifying. So the time passes and there is still some empuzzlement here. And let me outline what the question is about with the singular versus time dependent, how to model it, and how actually the Shima's model represents immersion freezing using this very theory. So the starting point is the Poissonian process of independent events. Here we I'd say that the theory was given already in the big 1933 paper. It was later, let's say, reinterpreted, but what is there kind of applies. So we start with a Poisson process, cumulative probability P, exponentially related to a rate and time. So after introducing J hat nucleation rate as a function of temperature, temperature profile as a function of time, and INP surface of this aerosol acting as nucleus A, we put it onto the right-hand side and we assume factorization into a term that is dependent on the surface and the term that is dependent on the temperature through the J hat rate and time and hence temperature. So in modern modeling, this I of P term would often be interpreted as a surface density. So this multiplies A, the surface. So this has units of 1 over surface. This is the usually called an S number of active sites, density of active sites for ice nucleation, and is parameterized as an exponentially linear function from experimental data. For example, widely used work of Niemand 2012 as in the Shima's model. So we have this probability defined as particle surface A and freezing temperature T. So we know that even for a monodispersed A, single value A, we get a spectrum of freezing temperature. So with such a spectrum of freezing temperatures, we look at how a particle-based simulation looks like. So here, a domain, X and Y, spatial dimensions, we populate the domain with particles, and we assign the particles with attribute denoting the freezing temperature using this very expression. So we take the probability density function, we sample it, and we have freezing temperatures that will trigger immersion freezing of these particles. So this function actually has a non-trivial, I would say, shape. So here I'm plotting a PDF constructed from this CDF for log normal A. So we have log normal size distribution for the INP, and we plot this PDF, the number of particles for a given freezing temperature and soluble surface. For a very narrow distribution, this is how it looks. And then when we made the log normal of A broader, we see that the distribution looks as follows. So how this non-trivial shape affects actually freezing. So on the right-hand side, it's a simple box model or a single grid cell of CFD simulation. On the x-axis, temperature, on the y-axis, frozen fraction, kind of similar to Vonnegut's plot, just we have temperature here, but the experiment just sweeps through temperature, so it is also effectively time. The dotted connected red black dots are result of Monte Carlo simulation. Monte Carlo meaning that we sample randomly from this distribution, we lower the temperature, and we check which freezes, which does not freeze. So the dashed lines depict the CDF for monodispersed A. So if we move back to an almost monomodal distribution, we see a match with the red line, so behaving as monodispersed. With increasing spread of the values, we have a deviation from the monodispersed line, and for reference, we are plotting here 10 times median and 10-fold smaller median values, depicting that the inclusion of the INP spectrum width in simulations or omission of this INP spectral width creates a limitation for such simulations because they will feature a different spectrum for freezing than monodispersed. And this is kind of as a comment to the simulations presented in Shima's work. Moreover, here we essentially depicted that the singular particle-based model is capable of representing also polydispersed INP. So while referring to this model as singular, I mean that we attach the freezing temperature as attribute to each particle, initializing it by random sampling from this probability distribution with a log normal A, for example. However, this size of the INP, the A, is not a particle attribute. It's just used for initialization and can be discarded later on. Freezing occurs if temperature of ambient air goes below the freezing temperature associated with given particle at time 0. So the freezing temperature is a kind of singular property of the particle. For time-dependent approach, we kind of back off a bit. We also do the same sampling from the same distribution for A. However, that's it. Later on, we evaluate the probability of freezing using our P in every time step. And given this probability, we decide if we freeze or not. So this gives us a possibility to validate our singular model with something that is more fundamental, let's say, from the point of view of this Poissonian description. So this is the same sets of simulations with teal points depicting time dependence. So narrow distribution, wider distribution, nice match. We have validated the singular approach. So now let us just remark that this was for cooling rate of 0.5 Kelvin per minute. When we switch to 5 times shorter, 5 times slower cooling, sorry, or 5 times faster cooling, they stop to agree. So why? Let's go back to the equations. Here, the temperature as a function of time. Let's plug the cooling rate, let's assume linear for now, into the integral. The cooling rate C goes out of the integral. And now we have the I of T, this is the singular parametrization, and J head of T of temperature, which we use in temperature dependent. So taking the temperature derivative of both sides give us a way of comparing the singular parametrization as a function of temperature and the time-dependent nucleation rate with the cooling rate parameter. So plotting x-axis temperature, y-axis these terms on right-hand side and left-hand side, we see that the dashed or dotted black line, the singular parametrization that we have used, matches the time-dependent one with solid lines only for single value of C, with depicted by thickness of the line, and only for one material type. The color denotes material type. So of course, material type is expected. We have different parameterizations for mineral dust, for bacteria, etc. However, the cooling rate here is something that we might think it's a problem. So is it really a problem? And well, this is nothing new. Let's maybe start with it. A very similar analysis can already be found in Valley and Stansbury 66 paper. There was a model described later on that introduced this cooling rate into the definition of this probability. But still, the point is that it's the singular ansatz, let's say, of assigning a specific temperature of freezing to a droplet at time 0 that is the bottleneck here. So whatever model we use, it might use the cooling rate of some value. It will not be the cooling rate that the particle encounters in a complex flow in its history of all its lifetime in a cloud and aerosol-cloud interactions included. So how to check if it's really a problem? So here we took a particle-based microphysics code with a prescribed flow test case, also known as TID 2D. So this concept of the kinematic test dates back to 90s work of Getzelman and Arnold. It was adapted for stratiform case as here by Hugh Morrison and Wojtek Grabowski in 2007. Together with Ania Ruga, we adapted it for particle-based simulations. Later on, it was adapted into the SKID 2D system for benchmarking microphysics. And here we use an Arctic stratiform cloud settings with the same framework based on the Shima case described by Unfrieden et al. 10 years ago. So basically, we have a single eddy prescribed flow, just mimicking what's happening in a stratocumulus or stratus deck. And we populate the domain with particles, assigning this freezing temperature as attribute. Let me just note here that for this study, the Lagrangian component uses the PySDM Python package for representation of cloud microphysics, and the Euler component using the PyMPData Python package for representation of the advection and scalar conservation equation. So these are two new packages that can be installed using the Python package infrastructure. They are both open source, pure Python, multi-threaded, and let's say Jupyter and Colab friendly. So let's look how the simulation looks like. Here's some snapshots of evolution. I'm going with time forward. What you see by the color of the particles is their size. So below cloud, we have aerosol of sizes of the order of 1 micron. In the cloud deck, we have sizes up to 10 micrometers. Inside, we see some interstitial aerosol that is resolved in such simulations, hence also suitable for aerosol-cloud interactions. And we run it as a spin-up until 10 minutes, after which we turn on the immersion freeze. And for simplicity, the particles after freezing retain frozen and nothing happens more with them, they become traces. So this is highlighted with gray shading of grid cells in this simulation. So here, when time goes forward, you will see that some of the cells, particularly in the top part of the domain, when it is the coldest air, start to freeze and then they become tracers. So this is just to picture how it works. Let's analyze output from 3 different flow regimes: almost quiescent flow, the previous one, and vibrant flow, to check the different cooling rates. And let's compare singular approach with freezing temperature as the attribute and time-dependent approach with the J hat, the nucleation rate, evaluated for a given size of the particle, that is the attribute. So the surface of the particle, ice active surface, is the attribute, evaluated in each time step. So here are the results. The 2 plots on the left, A and B, are constructed as follows. X-axis is the cooling rate here droplet concentration. The y-axis are shared. This is simply occurrence count. So how often we find a given value in the domain. So this plot with the 3 colors denoting 3 regimes of the flow, blue, fast moving one, red, the almost steady flow, show us that there is no single cooling rate in the domain as expected. We have a range of cooling rates. Dashed lines, solid lines, here not visible, here almost not visible. The third plot shows a difference, denote singular versus stochastic approach, or singular versus time. The middle plot shows what are the droplet concentrations encountered in the domain. As expected, changing the kinetics of the flow changes the activation efficiency. So we have more or less droplets activated. Finally, the number of crystallized particles on the right-hand side. So we see that the 2 representations of the very same population of particles, so same log normal surface of particles, give pronouncedly different results in terms of efficiency of freezing. And this is in agreement with the Fox model results presented earlier. So for slow cooling rates, the singular model will underestimate the number of nucleation events with respect to the time-dependent one that are based both on the same Poissonian model, same log normal distribution. Just to mention, it's not for free. The time-dependent approach is on average 3-4 times more costlier than the one due to evaluation of the probabilities and shuffling of random numbers in each time step. So coming to the final slides, implications, summary, and what's next. So here I'm bringing a recent 2021 opinion paper in ACP by Mary, Corslow, and Phil. And they point out that looking at the spread of sensitivities of climate models for the warming or for the doubling of CO2, so basically for perturbing climate and how the climate goes to a new equilibrium given its old feedbacks and dynamics, it's becoming clear that the cloud phase feedback, this is the keyword here, contributes substantially to the uncertainty in predictions of the rate at which our planet will warm in response to the increased emissions. So here there are 3 panels showing cartoons of scenarios for high INPKs low INPKs and dynamically increasing INPKs with no warming or CO2 change. So this is in follow-up to the prediction that the two models actually we show predict different efficiencies of freezing. And let's try to extrapolate it, what would come when we consider much more sophisticated systems. So the core physical process here that drives the so-called cloud phase feedback is the transition to clouds with more liquid water and less ice. So here we have a lot of ice in the cloud, less ice. The cloud with more ice precipitates more readily, it has shorter lifetime, and this one is expected to have higher albedo, hence strong negative feedback with respect to warming of the climate system. With low number of ice nucleating particles, the original state is already quite free from ice. So making the isotherm, zero isotherm or whatever isotherm, moving it upwards does not change much the picture. So depending on the abundance of INPs in the atmosphere, we can expect strong or weak negative feedback. And keeping everything constant otherwise, but just increasing INP, we can also expect that this cloud will actually be the shorter-lived mixed phase cloud in which occurrence of ice might trigger precipitation earlier, etc. So the authors underline that the models need to improve the representation of ice-related processes, in particular the need to include a direct link to aerosol type, specifically INP. And this is the very thing that particle-based models are good at linking aerosol properties with cloud processes. Finally, the models must also represent the INP removal processes. So this bidirectional thing that not only the aerosol influences the clouds, but clouds influence aerosols. The last slide. With this talk, I wanted to highlight the emergence of comprehensive mixed phase particle-based aerosol cloud precip models, including the model of Shima, but also concurrent efforts, for example, the Max Snow from German Weather Service or the developments at DLR. I think that one of take-home messages I would love to put here is that the probabilistic nature of the particle-based method is very suitable for stochastic representation for processes such as nucleation, collisions, break. In this very project, we introduced so-called water activity-based immersion freezing model-based time-dependent particle-based immersion freezing model with box example, 2D examples. We showed the role of the INP size spectrum in the process, as well as the fact that cooling rate that is embedded in widely used INAS fits translates to limited robustness of the singular model to different flow regimes. Particle-based scheme, moreover, in general, both singular and time-dependent, resolve the INP reservoir. So they are capable of capturing parts of this bidirectional aerosol cloud interactions. Next step is to actually leverage the key potential of the particle-based models by representing diverse INP populations. So we have many particles, we can represent many types of particles. And then, of course, informing larger scale models with results from such detailed particle-based simulations, which will be a great goal for these tools. Let me finish with thanking ASR DOE for funding, University of Illinois for hosting this work. All the codes that were used for the simulations presented are open and available on GitHub at this address. And thank you for the invitation and for your attention.